Hey folks, Mrs. White here. Today we're going to do a Chapter 12 review because when you folks are ready and or going into next week, you will be taking your Chapter 12 test. Now, unlike the Chapter 11 test, I'm not giving you a full week to work on this. Instead, I need it in by Wednesday night at midnight. That way I'm able to roll out your final project information to you on Thursday, the 21st. And you have 2 weeks to get that final project done. So what's nice is that this review and the Chapter 12 test is the last test. You're not going to have a final. And clearly the last test is only going to cover this chunk, and then it will get averaged with your Chapter 11 test. The Chapter 12 test, I believe, has 6 or 8 problems on it. So again, less than 10 problems. And it's going to cover all of the items we're going to discuss today. So what is on the test? We're going to talk about the 4 different tests that we technically have. It's kind of like 3 tests, but they're 4 different names. We'll do one of each together, and they will be in kind of a random order. And then I will show you the optional review stuff that I have online. I just want to make some more stuff available to you if you wanted to practice more and this wasn't enough. Your homework is to study as needed. Obviously, I'm going to have nothing due, but I would like a parent to email me when you're ready to take the exam. Remember, this is the last test, and I need you to be taking it and finishing it by Wednesday the 20th, which is next Wednesday. Okay, by midnight, I need those in so that we can get going on our project and you have enough time to complete it without feeling like you have to be doing 2 things at once. So the test that we're going to be looking at and that you're going to have to be labeling on your exam when it says which test are you doing is the goodness of fit test, which is when you're testing a distribution, and we use the word distribution usually in the directions, or they're actually showing you a table that's a distribution and you're doing a hypothesis test of that. Now that's the goodness of fit test, and this is section 12.1. I don't want you to pull right out to your notes every time. I want you to try to do it with just the materials provided. So you'll be able to use your book insert, and you'll be able to use that same little note sheet that Miss Ross provided for the Chapter 11 test. You'll be able to use it on this Chapter 12 also. So I'd have that out as you're practicing. Next, we have these 2 tests, which were both section 12.2. And they actually have the same keystrokes, but they're different names, and you actually write your null and alternative a little differently. So I thought that I'd include them as kind of separate things, even though the keystrokes for the actual numbers are the same. So first off, we have a test for independence, which means that you're going to have 2 variables in your contingency chart. Okay. On the left will be a variable, and across the top will be a variable. And you're going to be asked if there's a relationship or an association between the 2. Okay. And that's what you're actually determining. Is there a relationship between these 2 categories, or an association between the 2? So those are kind of your key things that you're going to look for to know that you're testing for independence. It'll be a contingency chart with 2 variables on it, and they'll say something about to figure out if there's a relationship between the 2 or an association between the 2. Same keystrokes, different name, the homogeneity of proportions, which means that you're comparing different populations or different samples to determine if they are equal to each other. Okay, and again, it's the same keystrokes as the test for independence, but on the left-hand side of your contingency table, you'll look at whatever you're measuring, and across the top, those columns will all be whatever your samples are. So sample 1, 2, 3, group 1, 2, 3, but it should be 2 or more populations, obviously. Otherwise, you wouldn't need to do a test this complicated. And your null and alternative need to reflect that you're determining equivalency. You're trying to see if all the samples are the same or not. You're not trying to define a relationship amongst the samples, just are they equal, yes or no. The last one is McNemar's test, which was section 12.3. Which has you looking at 2 dependent proportions, and they're going to be set up in a contingency table again, but it's going to say success and failure on them. Okay, so that is kind of your clue right in there. Is you're going to have 2 dependent proportions, which means they're going to be happening to usually the same people or the same sample, and you're going to have a group of successes and a group of failures, and you'll go through a McNemar's test, which is section 12.3, to do your hypothesis testing for that. Okay, and in this one, it's equal and not equal, kind of like up here with 12.2. And we also end up seeing that a little bit depending on what you're looking at in 12.1, but you can define 12.1 with words, and you would do homogeneous proportions in words usually too. Actually, I got those 2 flip-flopped. Anyways, you're going to see an example of each of these 4 things, so we'll make sure to clarify. the biggest part right now is going to be making sure you can identify which strategy to do and then hop into actually doing that calculation. So I have 4 problems here, one of each of these strategies, just so we can review a little bit of each, and you have to practice identifying which one are you doing. All right, so let's start off by looking at this problem. The General Social Security asked a random sample of adult Americans with children 2 questions. Do you believe there should be paid leave for childcare? And do you believe that children are a financial burden on their parents? Results of the survey are in the following table. Does the sample evidence suggest there's a difference in the proportion of adult Americans with children who feel there should be paid leave for childcare and the proportion who feel that children are a financial burden to parents? Use a 0.05 level of significance. So if we look here, these 2 questions are 2 variables, okay? And the samples, okay, are dependent because they ask the same people 2 questions. So this is actually a dependent sample, and we're looking at proportions. So this is going to be section 12.3, and this is going to be, you could write either dependent proportions or 2 dependent proportions on your test, or you could write McNamara's test. Okay, it doesn't matter to me whether you write this as the test we're running or this as the test that we're running. Either way, it works. Okay, so if we are going to run that test, the first thing that we need to do is we need to make sure that it is dependent and random. We know it's dependent because we identify that they're asking 2 questions to the same people. And they do say that they asked a random amount of adult Americans. So 1, it is dependent and random. We're good to go. The second thing that we need to test for is are our non-matching, so our yes and our no combination, so disagree and agree, and this one is agree and disagree, okay? Are those 2 errors going to be greater than or equal to 10 if we add them up? Well, clearly if I add those, it's going to be over 600, and 600 is bigger than 10, so we're good to go. You need to do those 2 tests first. After you do that, you're ready to write your alternative and your null. And I am going to go through these kind of quickly because it should be just a review. In these, what we're looking at is proportions being equal for always for our McNamara's test when we're doing 2 dependent proportions, okay? So the proportion of people who think there may be a financial burden and the proportion of people who think that they should be getting paid leave. We would assume that those are the same. That's always our null, is that they're equal. The alternative is going to be that they're not equal. Okay, so the proportion of people who think that they're a financial burden and the proportion of people who agree with paid leave are not equal. Okay, and that's going to be what we're actually testing. They did give us an alpha of 0.05. So now that we've done that and we know which test we're going to be running, we're going to go into our calculator, and we are going to run our chi-squared CDF test. Sorry. Now, before we actually can even do our chi-squared CDF test, you need to be able to put in your lower, your upper, and your degrees of freedom, which is always going to be 1 here. But we don't know our lower yet because that needs to be our test statistic. So, to get our test statistic, we actually have to do a little bit of work. It's not super duper crazy, but we're going to look at these 2 errors again. And this has to be done by hand, okay? You're going to take your 616 and your 64, and you're going to subtract them and square it, and you're going to put it over the sum of the 2 errors. So we end up getting like 304,704 over 680, which ends up being 448.0941. And that's our test statistic. Now again, this is going to give us our p-value. I wasn't super specific with this earlier. I just said, oh, we'll hop right onto the calculator. That you also could do it with classical method. Okay, but either way, you have to calculate this test statistic by hand. If you're going to be hopping on your calculator to do the p-value test right now, then, like I said, we'll go into our chi-squared CDF test. So we do that by going under our distribution menu. And we're going to go all the way down to chi-squared CDF. And then our lower is going to be our test statistic, which was 448.09. 41, but we'll just leave it as 09 for now. 1E99 is our upper, and again, we use degree of freedom as 1. Now, if you look, we have 1.8, but I do want to bring your attention to the fact that it says E negative 99, because what that means is you technically have 98 zeros in front of this. So this is pretty freaking close to 0. So we're going to assume that our p-value here, when we go back into our problem, is going to be pretty much 0. Okay, and you can write that. You could write 0 4 times after a decimal point to show me that you understand that even though there's 98 zeros, you're not going to write them all. That would be crazy. Okay, so we're essentially comparing 0 to our level of significance, which is 0.05, and yes, it is smaller. So the yes means that there is enough evidence to reject our null. So what we would say is there is enough evidence at a 0.05 level of significance to suggest that the proportion of adults who believe that children are a financial burden to their parents is different than the proportion of adults who believe that there should be paid leave for childcare. And to be honest, when you hear that conclusion, that kind of makes sense, right? Like the people who think it's a burden would probably be different than the amount of people who think that we should provide paid leave. Okay, those are two very different perspectives. If we were to do this using classical method, we're going to have to go into our chi-squared distribution. What's nice about chapter 12 is everything is chi-squared, so you don't really have to worry about making sure you choose the right table. You're always going to use table 8. So we'll go in, let's find table 8 right here. Our degrees of freedom, again, are 1, because that's what we're always going to use. And we're going to go over to 0.05. And we see that our critical value is going to be 3.841. So that means this value right here, where chi-squared is 3.841. And we look and compare that to our test statistics. So is 448 going to be in the shaded region? Heck yeah, it is. It's very much so in that shaded region. So we end up getting the same conclusion. So again, this is our critical value. It's the chi-squared that's tied to 0.05. And we would compare it to our test statistic, just like we would use that test statistic here to actually calculate our p-value. And this test statistic, right, has to be calculated by hand by looking at the difference of your errors squared over the sum of those two errors. So that's how we would tackle that problem. Let's take a look at 13. So in 13, they're looking at seeing if e-cigarettes assist in helping individuals quit smoking. So researchers found 300 current smokers to volunteer in the study, in which each group was randomly assigned to one of 3 treatment groups. Group 1 received an electronic cigarette, and the cartridge contained 7.2 milligrams of nicotine. Group 2 had one that had 5.4 milligrams of nicotine, and Group 3 had one that had no nicotine. So the subjects did not know which group they were assigned to. During the course of a 52-week intervention, a lot of them dropped out of the study. At the end of the study, 65 subjects remain in Group 1, 63 in Group 2, and 55 in Group 3. So if we added up Group 1, Group 2, and Group 3, that's the only ones that they actually gathered the data from. So the fact that they had 300 people, I think they mentioned up here, is not going to be part of any of our calculations. Okay, that's just extra information. They're telling you some people dropped out. We're actually not going to let that influence our calculations. Okay. So here are the results. They don't give us a chi-squared. There was a second part to this problem, but I decided not to include it here because I thought we would do exactly what you're going to be seeing on the test. So what you should notice right now is that there are actually 1, 2, 3 different samples. And they're all part of the same experiment. So if there's 3 samples and we're trying to figure out if they are all the same, okay, and that's what we would be doing. If we're given more than 1 samples, we're figuring out if they're the same or not. This is going to be section 12.2. And this is going to be specifically the homogeneity of proportions. Okay? And that's going to be the test we do. All right? So to do this, we're going to start off, what we would normally have to do is check our expected values and figure out and make sure that they're all greater than 1. And then we'd also have to make sure that if there's any that are less than 5, that it's only 20% or fewer. So that's a lot of work to do these expected values for this type of graph, and our calculator will do it for us. So we're going to wait to clarify our number 1 and our number 2 to make sure that this test is actually going to be valid until after we run our test itself. So we'll start off by writing our null and our alternative instead. Our null is always that there's no change. Now there are 3 groups, so I would say something like the proportion from group 1 is equal to the proportion in group 2, which is equal to the proportion in group 3. So again, we're checking to see if all 3 of those proportions are the same. The alternative is that at least 1 is different. Okay. It doesn't matter which one it is, but if one of them is different, then this is not true at all. Okay? So, we'll start off by getting ready to run our tests. We get our test statistic from our calculator along with our expected values. So to be able to run the test, we actually need to put all of these numbers in a matrix. So we're going to go to our calculator. We're going to go into our matrix options. So we're going to go see how it says matrix here. We're going to do second matrix. We're going to go over to edit. And we're going to change it to actually this is a 2 by 3, so it's perfect. So I'm just going to go down and start editing these values. So in that first cell, if I take a look, it's going to be 52, and then 54, 51, oops, 51. 254, this one's 51. Down to 13, over to 9, and then lastly we have 4 there. So I have all of this in. Now I'm going to use my chi-squared test. So I'm going to go to stat, I'm going to go over to tests, and I'm going to go down to chi-squared. And even if you forget to do the matrix, when you get to this point with the chi-squared test, you're going to be like, oh, I need to go into my matrix. Okay, so your observed should have been in matrix A. It's going to create the expected in matrix B, which is what we're going to go look at afterwards, and then we'll calculate. So our test statistic is 3.95956, so 0.9596, and our p-value is 0.138. So we'll put those in here. Our test statistic is going to be 3.9596. And our p-value that we found from there was 0.138. Now, if we're talking about being able to quit smoking, they did not give us a alpha value, okay, or a level of significance. So we would need to choose. Okay, so the more severe something is, the lower that number should be. So it would either be 10%, 5%, or 1%. Even if you took being able to quit smoking as the most severe thing and compared it to 1%, or the least severe thing and compared it to 10%, this number is bigger than all of them. So whether we did 0.05, whether we did 0.10, or 0.01, okay, this number is larger than all of them. It's going to definitely be a no, which means there's not enough evidence at a point whatever level of significance, okay, there's just not enough evidence to say that at least one is different, okay? So we would instead continue to accept the null at this point until we had an opportunity with more evidence, okay? So we would say there's not enough evidence. It'd probably be 0.05, right? It's not life or death. So there's not enough evidence at a 0.05 level of significance to say that the 3 groups reacted differently. Okay, which makes sense. I mean, look, they are pretty darn similar. Now, if we were doing it classically, we would have our chi-squared graph. We would find the chi-squared value that has to go with probably 0.05, and it's 7.8 if we were to check our book, okay? Our degrees of freedom is going to be, if there's 2 of these, we would use 1. And we're going to times it by, if there's 3 of these, we're going to subtract that by 1, and it's going to be 2. So our degrees of freedom we'll use is 2. And I'm sorry I didn't review that. When we're doing this test, you take however many rows you have, subtract it by 1, however many columns you have, subtract that by 1, and find the product. So if our test statistic is 3.9, clearly 3.9 is not in our 7.8, which would be our critical value for a chi-squared of 0.05. Okay, so both of these give us a hard no. Now we should go back and check number 1 and number 2. I'm going to show it to you this time, but in the next time we do this test, we're not going to go back and double check. To make sure that all of your expected values are what they need to be, you go back into your matrix menu, and you're just going to go down to B, press enter, and then enter again, and that shows you your values in there. So what we're looking at is making sure that there are no values that are less than 1, so everything has to be bigger than or equal to 1. And they are 47, we got a 7, a 54, an 8, and a 55, and a 9. And then we can't have more than 20% of these values being less than 5. And none of them are less than 5, so we're good with both 1 and both 2. So those would be the two assumptions we would have to make, and that would have to work in order for us to do this specific hypothesis test. All right, so let's take a look at number 9. Are health and happiness related? The following data represent the level of happiness and level of health for a random sample of individuals from the general social survey. So we're looking at 2 separate variables, okay, and we're trying to find if health and happiness are related, and that's one of our keywords. If we have 2 variables and we're looking to see if they're related or associated, we're doing a test for independence. And again, that's going to be the same keystrokes we actually just did, but our null and our alternative are definitely set up differently. So our 2 assumptions that we like to do first have to do with our expected values, and we're going to get those from our calculator afterwards. So instead, we'll hop right into our null and our alternative. And this, again, is where it varies very much from the previous example, right? When we did this problem here, our null is that they're all the same, and our alternative is that at least one is different. Well, when we're testing for independence, okay, our null is going to be that they are independent, which means they are not related, okay? So we would say health and happiness are not related, which means that they are independent, okay? Our alternative is that health and happiness are related, right? We can assume that they are separate until we find evidence to say that they are. Okay. Now this is kind of the opposite of what our test for homogeneity did, right? Our null was that they're all equal, and our alternative was that they're different. So you just have to be careful here and make sure you set up your null and alternative appropriately if you're doing a test for independence. Okay, so the null is that they're not related, they're independent from each other, and the alternative is that they are related, okay, which means that they are dependent. So to do this, we'd have to take this whole shebang and put it into a matrix in our calculator. If you want to, you're welcome to pause the video right now and plug those into matrix A. I already crunched these numbers, and I'm just not going to do it now to try to save some time in this review video. After you've put those into matrix A, you're going to go in and you're going to do a chi-squared test. And when you run the chi-squared test, you're going to make sure it's A and then B. And then it is going to ask you to put in your degrees of freedom. Now remember, degrees of freedom are this minus 1 and this minus 1. So there's 3 rows. So it's going to be 2 times, there's 4 columns. I'm going to subtract 1, which is 3. So our degrees of freedom is going to be 6. So if I type 6 in for my degrees of freedom, matrix A, where I put this into, is where I'm going to put my observed data. My expected is going to get put into B. Then I'm going to press enter. I'm going to get a test statistic that says 182. So chi-squared is our test statistic. And it's going to be 182.1737. And they will also give me a p-value. It's going to say 1.17, but it also has an e with a negative 36, meaning that we'd move this 36 places forward. So it's pretty much 0, right? There'd be 35 zeros before this one. If we compare that to our 0.05 level of significance, that is clearly smaller, so this inequality is true. That means there is enough evidence to accept the alternative and reject the null. Okay, so we would say there is enough evidence at a 0.05 level of significance to say that health and happiness are related. Okay, If you were to do this using the classical method, we find our chi-squared value for 6 degrees of freedom. And if you looked that up right on our table, 6 degrees of freedom, 5%, it's going to be 12.592. 12.5, and clearly 182 is way, way, way in the shaded region. So again, this one is another yes, which just reinforces the p-value test. So let's take a look at our last problem here, okay? And this is like as hard as these will possibly get. Religion in Congress. Is the religious makeup of the United States Congress reflective of the general population? The following table shows the religious affiliation of 535 members of Congress with the religious affiliation from a random sample of 1,200 adult Americans. So they walk you through all the steps you would have to do here, but because we're not looking at a contingency table, okay, we're looking at a distribution of members, we're going to be checking a goodness of fit test. Whenever you're dealing with a distribution, which means all of the different groups, you're going to be doing a goodness of fit test, which, if you need to review it more, is in section 12.1. Now, there's a good potential you're not going to be given raw data twice. You will potentially be given a percent of expected, okay, and then some actual observed data. Like, for example, this is the observed data. We need to calculate the expected here, okay? That's something that you have to do. You don't have a choice when you're doing a goodness of fit. And then your observed data will go in L1 and your expected will go in L2. So it's actually kind of a task to figure out expected in a problem like this. The expected value is not 306. This is out of only 535 people. This is out of 1,200 people, okay? So our expected value is actually the percent that this represents of the 535. So if we did 306 divided by 535, we'd actually get 0.572, which makes sense, right? A little bit more than half. Okay, we would take that decimal to get our expected value, 0.572, and times it by our sample size, so 1,200. So if I actually multiplied those out, I'm going to get approximately 686.4 people. So if we ask 1,200 people, and it's going to be the same proportion as the number of members of Congress, okay, it should be about 686 people. Okay, and you can see that data is kind of close, so it'd be good to actually do this hypothesis test to figure out, is it close enough to say that it is reflective of the population or not? So first things first, in a problem like this, we have to go through and find all of our relative frequencies here. Okay, all of those decimal values. And I actually went through and did that. So this one would be, if I just did 164 divided by 535, it's going to be 3065. This one's going to be 0.0299. This one would be 0.0093, and so on and so forth. Then we're going to take each of those decimals, right? Okay, and we're going to times it by the amount of people surveyed. So again, if I did it for the next section, I took 0.3065 and multiplied it by the 1,200, I would get 367.8. So that seems a little bit high compared to this. I should go through and get the rest of these. So my next few values are going to be 35.88. The next one is 11.16. Underneath that would be 62.76. Instead of 57, this one actually, based on this number, okay, it should only be 13 people. So that seems like a big difference, 13.44. And then the last one is 22.44. So again, those two seem like a really big difference. Those two alone could make our null and alternative kind of cancel each other out. Oh, we didn't even write our null and alternative. My bad. Sorry, folks. Our null is going to be that they're the same, right? So we would write that religious affiliation is the same. And our alternative is going to be that they are different. Okay? And let's see, did they give us a level of significance here? Nowhere here did they give us a level of significance. So usually the alpha then would be assumed to be 0.05. Religious affiliation really isn't high risk. I mean, you could choose 0.05 or you could probably choose 0.10 and it wouldn't matter. Okay. It's not like life or death, so you don't have to have only a 1% chance of an error. So now that we have this, we're ready to do some work and figure things out. So we are going to put all of this information, our observed actual data from the actual sample they took, and put it in L1. We're going to take all of these values, okay, our expected values, and we're going to put them right in L2. After they're in L1 and L2, we're going to do a chi-squared goodness of fit test. Okay. So I do not have them plugged into my calculator. It's going to take a lot of time for me to type those in. So instead of doing that, I did do it before starting this video. So if I ran through and made sure that L1 was for observed, L2 was for my expected values, type in everything I need to, run my test, I'm going to get that my test statistic, which here again is chi-squared, is going to be 1,500.242. And that my p-value is 0. It says that it's 0 right on there, okay? It doesn't matter how small it is or what the exact value is. They literally just gave you 0. And 0 is less than 0.05. So far it says there is enough evidence. So we would say there is enough evidence at a 0.05 level of significance. If they don't give you an alpha value, you can just say there is enough evidence to say that the religious affiliation of Congress and residents are different. Okay. If you were doing the classical method, you would have to look up a chi-squared for 6 because there's 7 groups here. And we would just subtract 1, so we would use 6 degrees of freedom, which again is going to be 12.59. We just did the 6 degrees in the previous problem. And then 1,500 is clearly in the shaded region, but it's way the heck out here. Okay, so again, is it in the shaded region? My answer would be yes. That means there is enough evidence to reject my no. I would say that there's enough evidence to say that the religious affiliation between Congress and the residents of the U.S. are different. Okay. Now, I know that was somewhat quick, somewhat slow. Hopefully it was enough review so that you are ready to tackle either more review questions or you're ready to maybe look over the homeworks you've done so far and study for this exam. If you have any questions, please attend office hours tomorrow from 4 to 5 p.m. I'm happy to do more problems with you or answer any specific questions you have, but I am not holding office hours next Wednesday because I'm hoping to just be answering individual questions about the test and having an opportunity to just correct the ones that are already in. Okay, folks? So last test, take your time, study. Make sure you have all your materials. You'll be able to use your book insert and your note-taking guide from Miss Ross again. Okay? If you need help, I hope to see you during office hours. Otherwise, good luck. Bye, folks.